I'd like to discuss the efficiency of simple machines. There's a very basic equation for calculating that. The efficiency of a machine will equal the work output over the work input times 100. This means your work output of any simple machine is actually going to be less than the work you put into it. We've discussed this before. Why would you want to use a machine if you had to actually put more work into it than you get out? And the reason is because, of course, work equals force times distance or displacement. And that means that there's two components of work. So you could actually exert a very small force over a long displacement and have the same amount of work that you would have if you had a very large force over a short displacement. So sometimes you're just incapable of exerting a certain amount of force. So we'd want to use a machine so we could use less force, even though we have to move it over a large displacement. And in the end, that might actually be more work, but it'll be easier work, I guess you should say, because it lessens the amount of force of the aspect of the work that you would have to be using. So another way to write this is the work output. Usually we call the work is force times displacement. So for work output, a lot of times we call it the force resistance, or the resistance force, which basically most of the time is the weight of an object times the distance that you're going to move the resistance, which almost always is the height that you're going to lift it. So the work output is usually the weight times the height that the machine is actually going to lift it. And we're going to divide that by the amount of effort force that you are going to exert on the object. So you might be pulling a rope on a pulley, or you might be pushing a box up along an inclined plane. That would be the force that you are exerting, your effort force on the object, times the displacement of the effort. So that might be how much rope you pull or how far up an inclined plane you are pushing it. Both times it's force times displacement. We like to kind of characterize these a little bit differently so we can remember them. Times 100, of course. So if I had like a pulley system, something like this, and there's a big weight attached on here, I could be pulling along this rope here with a certain amount of effort force, and I could pull it a very long displacement. But then right here you're going to have the weight, or what we would call your resistance force, and we're going to lift it up a certain displacement, and that displacement here is going to be less than the amount of displacement that you're pulling here, which means then this effort force would end up being less than the weight of the object. So that's why we'd use the machine, because we could use less force to lift a heavier force. Now we counteract that by pulling at a much longer displacement than how far it will get lifted. But this is the equation for efficiency of a machine, and we want to try to use that as we kind of examine a couple of problems here. So let's look at another simple machine. Let's look at an inclined plane. And so we'll draw an inclined plane ramp here, and let's say that this is a 30-degree inclined plane. So we have let's say we have 120 Newton weight, and I want to get it up to this floor level right here. So there's two ways I could do it. I could take the 120 Newton weight, let's say this is the 120 Newton weight, and I could just lift it up this height right here. That would be an amount of work it would take. That would be the work output. Or I could take the 120 Newton weight and I could let's put it a little further up here. I could push it all the way up along this side here. So I want to figure out what is the effort, or what is the efficiency of this machine, and I'm going to find out that the amount of force that I need to be pushing on this box, I'm just going to tell you, was 100 newtons. Okay, so to get the box all the way up the top here, it's only going to take me 100 newtons of force, rather than 120 it would take just to lift it. So I want to figure, so that's good, that's why I'm using the machine. So what would the efficiency of this machine be? Well, efficiency is going to be the resistance force times the distance that I'm going to move the resistance over the effort force times the distance that I'm going to apply the effort times 100. And if you remember, then the resistance force right here is usually just the weight. So that's going to be 120 times the distance resistance, which would be this side right here. Basically the height of this inclined plane. This would be the distance that I'm going to move the resistance force. And right now I don't know that, so I'm going to just leave that in there, distance resistance. All over the effort force, which you can see right here is going to be 100 newtons that I'm applying it, so I could have it over 100. Times this distance right here. This is the distance that I'm applying my effort. This is dE. And I don't really know that either, so I'm going to put dE there. And of course, if I did that, I could take it times 100. So how do I figure out my dr and my dE? Well, we actually have an angle of the inclined plane. And if I look at this angle of 30 degrees right here, the sine of this angle is opposite, which of course would be dr, over the hypotenuse, which actually would be dE. So the sine of, and I'll just leave it as, well, I'll just do it, sine of 30. Sine of 30 would equal the opposite side, dr, over the hypotenuse side, dE. And you'll notice that dr over dE is, I have that right here in my equation. So what I can do is I could take 120 divided by 100, and instead of dr over dE, I could take that times sine of 30 in this case. So I didn't actually have to know either of those sides because I knew the angle, which is the relationship between those two sides. So 120 divided by 100, of course, is 1.2. Sine of 30 is 1/2, so it'd be half of that. So I'm going to get 0.6, and of course I'll take it times 100. And the efficiency of this machine will be 60%. 60% efficient, which means I'm going to have to do more work, or I'm going to have more work output than, or more work input than I have work output. But that's okay, because I'm going to get to use less force than what it would take just to lift it straight up. So it's a 60% efficient machine, and I'll still want to use it because I am using less force to push it up the inclined plane. Okay, so this is why we would still want to use a machine. Alright, let's look at another one that's very similar to this. Let's take another inclined plane. And let's say we have, some angle here, theta. I'll tell you it's 15 degrees, but let's just think about it as theta for right now. And there's a box here that we're going to pull up the inclined plane. So right here is the effort force that I would need. Of course, this side, this whole side is my effort distance, and the height right here is my distance resistance. And the box has a certain weight. I'll put the box down here also. It has a certain weight of W. We don't actually know what it is. And I want to find what is the efficiency of this inclined plane. Okay, one more thing we have here is that mu friction here is 0.16. Okay, so we have an equation. It's the distance, or the resistance force times the resistance distance all over the effort force times the effort distance, and then we'll take that times 100 to get our efficiency. Okay, so we actually remember from the last problem we just did that dr over de is actually the sine of this angle. Sine of this angle would be the height over the hypotenuse. So, and the resistance force is the actual weight of the object that we're lifting. So, in for the resistance force, I could go ahead and put W over, and then I want to figure out what this effort force is. That's going to be the hard part. So, but dr over de, this part right here, I know is the sine of the angle, sine of theta. And we know that theta is 15, but we'll get back to that in a second. Okay, so what is all I need left to here is what is the effort force? Well, the effort force, this is going to be pulled up at a constant velocity. I guess I should have said that, which means that this force is going to be equal to any forces going down the opposite way. Of course, we have two forces going that way. We have the parallel force component of the weight, which always works down an inclined plane. And we also have friction, which always works opposite the motion. So if you remember, parallel force is W sine of theta, and that's parallel force. Friction force is mu W cosine of theta, because it's mu times the normal force. Okay, so I'm going to have to add both of those together for my effort force. So that'd be W sine of theta plus mu W cosine of theta. And I'd have a W that would cancel out on each term. So I would end up with, if I take this sine of theta right into that spot there, I'd have sine of theta over sine of theta plus mu cosine of theta. And of course, in the end, I'll take this times 100. But you'll notice here that all I needed to figure out the efficiency of this machine is what is the angle, which is 15, so I can put 15 in for my theta, and the mu, which was 0.16. I could put that in for my mu. And if you plug the mu and the angle of 15 into the equation, take it times 100, you'll get approximately 63% if I round it off. So I can figure out the efficiency, and I didn't even know the height and the effort distance. And in this case, I didn't actually even know the forces. I can kind of come up with an equation that I could use right here for any object which I'm pulling up an inclined plane at a constant velocity. That would be the efficiency of the machine. Hope that makes sense a little bit with efficiency of simple machines.